this is lesson 6 of unit 6 on antiderivatives and basic rules and notation for integrals. Okay, so we've kind of been working around this leading up to this section with the fundamental theorem of calculus, but we're now going to come up with some general rules for some well-defined functions that it's pretty straightforward to find their antiderivative and integrate them. But we're going to talk in more general terms about an indefinite integral. And then this unit will end with some special cases and how we find the integral of some functions that aren't as straightforward as the ones in this section. Okay, so let's get started. So we're going to start by understanding that if f of x is a function and it's an antiderivative of a small f of x, then f prime of x of capital F is equal to little f of x. Okay, so finding the antiderivative is called antidifferentiation. And the family of all antiderivatives is called an indefinite integral with respect to x. And what you'll notice is that it is going to look like this. It's going to have, we're going to take the integral, and it's going to be f of x plus c, where this is called the general solution, and c is the constant of integration. And what I want to point out is the fact that this c is an arbitrary constant. Now, the reason why I'm saying that is we're going to see that if we would integrate two separate integrations and then put them together, and they both have c's, we're still going to call the new constant when we add them together c. Excuse me. Because it's arbitrary anyway, and we just use c for constant. And if we need to find it, which we'll see at the end, there's a way to find that constant. Okay, so first off, if we know that the function f has an antiderivative, then there is a family of functions that will share the same antiderivative. They only differ by a constant of c. Now, we have that here. There is a family of antiderivatives for the function f of x equals 3x squared, and we're to list 3 of them. Now, what I want you to note is, first of all, if we were to find the antiderivative of little f of x, it would be x cubed. These are all graphs of x cubed, and you can especially see that as the one that goes through 0. That's our cubic graph. So let's choose that as our f1. So capital F1 of x will just be x cubed, because my c will be 0. And then f2 of x can be any of these. So let's pick like this one. So we have x cubed plus 5, and f3 of x, let's pick a negative one. Let's pick this one, is x cubed minus 5. Okay? And there's a myriad of answers you could put for this. But we're supposed to explain the meaning of c in your function. So as I mentioned, it's a vertical translation. So it's a vertical translation. And if c is positive, then it's translated up. I shouldn't, that's fine. If c is less than 0, then it's translated down. I just want to make sure I didn't say it in there. I should have used capital F. Okay, so given each derivative here in example 2, find the general antiderivative by guess and check. And I'm not going to have us guess and check because we have already done some of these. So I am just going to have you guys do these with the rules we've already developed in class. So if you want to pause the video here, I'm going to write the answers. Okay, so there are the antiderivatives for each of these, and if you notice, for every one of them, I have a plus c here, because we don't know exactly where it's going to be oriented on the grid. That's going to be determined by being given an initial condition. Okay, so moving on. So the expression, the integral of f of x dx, is read as the antiderivative of f with respect to x. So the differential dx serves to identify x as the variable of integration. And again, that comes into more important when you go into some later calculus classes. And we start doing multivariable calculus. So if you notice, we have our two notations for antiderivatives. And we're going to be using this a lot in Chapter 7, in Unit 7. Okay, so let's label everything in our antiderivative expression here. So first off, this first line goes to our dx, and our dx is, of course, our variable of integration. And right below it is the f of x. That section is called the integrand. Just like you have the dividend when you're dividing, that's the integrand. And then the c is our constant of integration, as we noted on the first page. And capital F is, of course, our antiderivative. Okay, so those are the different parts of our indefinite integral. Okay, so now we're going to discover some tricks to help us integrate easily. So the first one is to rewrite it. You want to think, like, this looks like it's hard because we have a cosine in the denominator, but if we rewrite this, what we're going to see is that this becomes 5e to the t plus this is the not inverse, is the reciprocal of cosine, and that is going to be secant squared t. And this is all dt, our variable of integration. So secant squared is a derivative. Its antiderivative is tangent. So our answer will then be 5e to the t. E to the t is its own derivative, plus tangent t plus c. And what you can always do is take the derivative of those two terms and see if you get the integrand back when you're done. The next one is you want to multiply and distribute. So you have, if I were to multiply that out, I would have 9x squared minus 6x plus 1 dx. And now I can take the antiderivative. And I get 3x to the third minus 3x squared plus x plus c. And then finally, separate the fractions if you can. Now remember, if there was addition or subtraction in the denominator, you couldn't do that, but I can do that. And I'm also going to rewrite it at the same time. So this becomes x to the negative 3 plus 4x to the negative 4 plus 5x to the negative 5, and that's all dx. So then integrating this, you get negative 1/2 x to the negative 2 minus 4/3 x to the negative 3 minus 5/4 x to the negative 4 plus c. So writing that with positive exponents, we get negative 1/2x to the second minus 4/3x to the third minus 5/4x to the fifth plus c. And then our last one is what we've already kind of did in the last one, is put different techniques together. So we're going to expand the top, and then we'll divide out the 1/2 x in the denominator. So we get x squared minus 6x plus 9 in the top, and then we have x, I'll write as x to the 1/2 in the bottom. And this is going to be rewritten as the integral of x to the 3/2 minus 6x to the 1/2 plus 9x to the negative 1/2 dx. And now we can find the antiderivative. and we get 2/5 x to the 5/2 minus 6 times, and then we'd have the 2/3 x to the 3/2 minus, I'm sorry, that would be plus 9 times 2x to the 1/2 plus c. So our final answer will be 2/5 x to the 5/2 minus 4 x to the 3/2 plus 18x to the 1/2 plus c. And if you want to write those as radicals too, you can. Both answers would be acceptable instead of using fractional exponents. Okay, now the next page is a list of the basic integration rules. So the first column says what you get when you differentiate, and the second column is what you get when you integrate. So when you integrate any constant, you get a constant, even 0. So that's what this is showing. If you integrate 0, you get a constant. If you integrate a constant, you get kx plus c. If you integrate a constant times a function, you can pull the constant out. And these come from our summation rules here. When you're adding functions or subtracting them, you can integrate them separately. And we've already talked about in class our general power rule, which is right here. And remember, the n cannot equal 1. And then, of course, all our trig rules are here. First, cosine, sine, secant squared, cosecant, cotangent, secant, tangent, and cosecant squared. And you'll notice, don't forget about that negative sign for the ones that when you took the derivative, you got a negative. And then our transcendental functions, we have our e to the x is itself. And then, of course, we've already seen a couple of examples where we're raising a to the x and 1 over x. Because remember, the derivative of ln of x is 1 over x, so its antiderivative has to be ln of x. If you notice here, they have the absolute value there, because remember that the domain of the ln function has to be positive values. Okay, so we're going to finish this off by doing one with initial conditions. So how do you get rid of the c? How do you find a specific c? And that's based on whether or not you have an initial condition. So for example 4, we are going to solve the differential equation subject to given conditions. And as I was mentioning earlier, this is how we're going to get rid of this c. And I will do letter A, and then you guys can do the other ones and check your answers then. And then we'll go over these and practice these in class tomorrow. Okay, so the first one, we have f prime of x equals 2x minus 1, and we have an initial condition of f of 2 equals 5. So this initial condition is how we are going to find our c, and we're going to worry about that at the end. So the first thing we want to do is integrate this and find the antiderivative of 2x minus 1. So when we do that, we are going to get x squared minus x plus c. So now we know that our f of x is x squared minus x plus c, and we're going to apply our initial condition. So we know that f of 2 is equal to 5, so we're setting this equal to 5, and we're going to substitute 2 in for x and solve for c. So what we have is that we have 5 equals 4 minus 2, which is 2 plus c. So c equals 3. So our final answer, and I'm out of room, I'll write it at the top here, is f of x equals x squared minus x plus 3. So that is solving the differential equation. And so you guys try the other ones, and then pause the video before you do them, and then you can check your answers. Okay, there is B, C, D, E, and F. And again, as I said before, we will go over this some more in class, and I will take any questions at that time.